Welcome to this puzzle session. Here is the problem. Fix a positive integer n and let S be a subset of the set of all the first two n natural numbers such that the size of S is n plus 1. So we have chosen more than half of the things here. We want to show that there exist two distinct members in S such that one divides the other. It's a remarkable fact that as soon as one chooses more than half of the things here, one will necessarily choose two numbers such that one is a divisor of the other. Okay? As usual, you're encouraged to pause the video before we look at what I'm going to discuss. And with that, now let us continue. So we will be invoking the pigeonhole principle ultimately, but before that, let me define a few things. So define these sets. A1 as 1, 2, 2 square, 2 cube and so on. A3 as 3, then 3 times 2, 3 times 2 square, 3 times 2 cube and so on. And similarly for all the odd natural numbers. So these are all subsets of natural numbers, of course. But the thing to be noted is that these partition the set of natural numbers. We may write this. So what does that mean? This notation just means to say that every natural number is in one of these AIs and exactly one of these AIs. Right? So you cannot have one natural number lying in A3 and also in A5. That's not going to happen. Okay. So since these AIs partition the natural numbers, we also have, this implies that the set S that we have is partitioned by these sets. But up until which point, we will be exhausted by the time we reach here. Because if you go any further, disjoint union A2n plus 1 intersection S, that thing is empty. A2n plus 1 has numbers strictly greater than any number in S. So all the further intersections are empty, so we are not writing that. So S admits this partition into these 2n minus 1, not 2n minus 1, into these n things. So A1, A3, up to A2n minus 1, these are a total of n things. Okay, so S has been broken down in n pieces. But what is the size of S? The size of S is n plus 1. So there are n plus 1 things in S, but we have broken down S into n pieces. So there must be a piece which contains at least two distinct members of S. So there exist two distinct things in S such that P and Q both lie in some AI for some I. But if P and Q lie in AI and P less than Q, then it follows that P divides Q. So this is a property that any of these AIs enjoy. If you pick two elements in A1 and one is smaller than the other obviously, then the smaller one will divide the bigger one. Same thing happens here, same thing happens here. So as soon as you have two distinct things lying in the same AI, one of them will divide the other. And that finishes the proof. So basically, the idea was to partition the set S into some very nice pieces, which require some inspiration. But it is also not a completely out of the box thought, because what we wanted to do was show that there are two things in S such that one divides the other. So clearly, if you've chosen some element in S and you've also chosen the twice of that element, then you're already done. You may proceed by trying to build the set S so that you never choose the double of anything that you've already chosen. And that naturally kind of leads to this kind of decomposition. A1 has things which are doubles of each other, A3 has things which are doubles of each other. And yeah, it requires some creativity, but it's also not completely out there. It's a very nice proof. There are other proofs of this. There is one proof by induction also, but let's not get there. So with this, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time. All right.